What's up everyone, welcome back. Patrick here, and moving on to the next video dealing with even versus odd functions. In this particular video we're given a bunch of functions and we have to show algebraically whether they are even, odd, or neither. And we're going to be focusing more on the algebra part, but if possible I'll also show you the graph of how it's going to look. One of these functions in particular, the one in part E, is going to be too complex to graph, but if you want, whatever result we get, you could check it in Desmos, how it looks like as well, and see if it satisfies those graphical properties that we went over in the overview video. And I'm assuming you've watched that video before watching this one. As a quick recap, if you remember, a function is going to be even if the property f of negative x equals f of x holds, and it's going to be odd if the property f of negative x is equal to negative f of x holds. So these are the two properties we're going to be testing, and then if neither of these properties hold, then it's going to be neither. All right, so starting with part A, we have f of x equals x cubed minus x. So first thing we check, what you want to do, let's actually do this in different colors. So we have the original function f of x. Because f of negative x is what's being used in both properties, that's the first thing that you want to get an expression for, right? And so what we would do is we would basically plug in negative x for all of the x values. These are like in brackets here. There's invisible brackets with those x values. And so you got to be careful plugging in this negative x. So instead of x, we would write negative x to the power 3 minus negative x, like that. Right? So we're just plugging in negative x for these x values in the original function. And then what we have to do here is we need to simplify this, right? Because right now we can't really compare it to the original function because it's in a different format. It's not simplified. There's all these like negatives floating around. So you have to simplify this. So if you remember that property, right? If you're multiplying two things in a bracket and there's an exponent outside of the bracket, you could take both things to that exponent. And then negative, negative, that turns into a positive. Now, negative 1 to the power of 3 just stays as negative 1, and then we have this x cubed over here, right? If it was negative 1 to an even exponent, like negative 1 squared or negative 1 to the power 4, negative 1 to the power 6, it would turn into positive 1. But negative 1 to an odd exponent, 1, 3, 5, 7, etc., stays as a negative 1. And so now we end up with a simplified function here, negative x cubed plus x. So this is the expression for f of negative x right here. And so what we want to do is first we want to compare f of negative x to f of x, right? The even property is always the one we check first because we already have f of x, right? We don't have to do anything with that. And so if you compare these, is this the same as this? No, it's not, right? Negative x cubed plus x is different than x cubed minus x. So we know that this property here, the even property, fails. So we know that this function in particular is not going to be an even function for sure. So then we move on to the odd property. Now, f of negative x, we just figured that out right here, right? It's negative x cubed plus x. So we have to check now, does f of negative x equal negative f of x? So this is the next expression that I'm going to get. And this one is really simple. All you do is you basically put a negative in front of the entire function, right? This is another way you could write it. You could put like a bracket here around the f of x, and you got this negative 1 on the outside. Well, f of x we are given, it's just x cubed minus x, and then to simplify it, you distribute this negative inside the bracket, and you would end up with negative x cubed plus x. So this green expression here is the expression for negative f of x. And notice that this expression, negative f of x and f of negative x, both of these are equal. right? And so this property holds, and so we know that it is an odd function, right? We just showed that f of negative x is equal to negative f of x. All right, so that is the flow of work with these types of questions. You're given the function. Next step, you find f of negative x, simplify it, see if f of negative x equals f of x. If it does, it's even. You could stop right there. If not, then you have to find an expression for negative f of x and then check, does f of negative x equal negative f of x? And if it does, it's odd. And it was odd in this particular case. All right, so that's how you show it algebraically. Now graphically, again, we're focusing more on the algebra part. But if you're interested, I mean, you could graph it in Desmos. Basically, the way this graph is going to look like is, well, we could factor this. So we could take out an x, and you'd have x squared minus 1, and then you'd have x minus 1, x plus 1. And we're going to go through polynomial functions in a future unit in more depth. So again, you don't need to know at this point how these graphs are looking. It's more so the algebra you need to know. But if you are curious, you have intercepts at 0, -1, and 1. And so if I was to graph this, it would basically look like this, approximately. And remember, an odd function, it has rotational symmetry, or it's symmetrical about both axes. Well, if I take this half of the graph, right, and if I reflect it, let's say above the x-axis first, I would get this graph over here. And then if I take this graph, or this part right here, and reflect it about the y-axis, I would end up with this other half of the function. Same thing if you went the other way. If you took this first half, okay, there's a lot going on here, so if I took this half and reflected it about the y-axis first, I would end up with this, and then if I reflected about the x-axis, I'd end up with this other half right there, right? And so when that's happening graphically, then we know it's an odd function. So again, not as important, but in case you're wondering, that's basically how it looks like. And maybe it is useful for me to go over these graphs because sometimes you'll get questions where they give you graphs and then you have to check, is it even or odd just from the graph, right? You won't have an equation, right? So graphically you could tell if I take this half in red, reflect it about both axes, I would end up with this other half. Moving on to part B, we have another polynomial, so f of x equals 2x squared plus 3x. So same process, let's first find what's f of negative x going to be. So we're plugging in negative x for all of the x values, so make sure you put them in brackets like that. So then you'll have here, okay, this -1, let's distribute the exponent 2. Like that, and then 3 times negative x is basically minus 3x like that. So this would be 2, +1, right? -1 squared is +1, x squared minus 3x, and then 2 times 1 times x squared, that's just basically 2x squared minus 3x, right? So this here, f of negative x, that is the simplified expression. First thing we check, is this equal to f of x? No, it's not. Right, so we know this is not going to be an even function, right? That property is failing. So the next thing we check, is it going to equal negative f of x? So negative, in brackets, f of x is just 2x squared plus 3x, and so distribute the negative inside the bracket, we'd end up with negative 2x squared minus 3x like that. So this is negative f of x right here. That's the expression. Is this equal to that, right? Is f of negative x, which is this in red, equal to negative f of x? No, it's not, right? The minus 3x's are equal, but notice here we have a positive 2x squared. Here we have a negative 2x squared. Okay, so these do not equal. So this property fails as well. So this function in particular is neither even or odd. One thing you could tell, like a quick shortcut, I mean, you still have to show the work and stuff, but it is useful, and I mention it in other videos as well, that for polynomial functions in particular, ones that are expanded, right? Not ones that are factored, like if you have x plus 3 times x squared minus 5, for example, right? A polynomial that has factors that are multiplying, which we'll go through in the polynomial functions unit. If a polynomial is expanded, what I'm about to say only applies to expanded polynomials. If you ever see a combination of even exponents and odd exponents like that, it's always going to be neither. Okay, so that's a quick shortcut for you to, again, you got to show the work, but it is helpful that maybe when you see something like this, an expanded polynomial, like if I see, if I give you, for example, 6x to the 5 minus x to the 3 plus x squared, right? Odd exponent, but here there's an even exponent, okay? And whenever you get that combination of an odd and even exponent in an expanded polynomial, right? And remember, polynomial, there's no like fraction, there's no variables in the denominator. That would be a rational function. So if you have like x squared plus 3 over x minus 4, if it's a rational function, this may not particularly apply what I'm saying. It's only if it's a polynomial, right? So it's just one line, no fractions or anything. I mean, you could have constants as fractions, but there's no variables in a denominator or anything. So just a regular standard expanded polynomial. If you see a combination of odd and even exponents, you know it's going to be neither. So if you think about part A, right, we had x cubed minus x. Well, notice that odd exponent, right? And then when we did the algebra, we ended up getting that this was an odd function, right? There was no mix of even and odd exponents. So again, not necessary to know that, but could be helpful for you to just look at it and just know what the final result is that you have to get, right? But again, you still have to be able to show this work, still have to be able to go through the algebra. And then if you wanted to make a quick graph of this, again, it's not necessary, but if you're curious to see how this looks graphically, right, I could factor this. And so notice this is a quadratic that's going to open up because the a value is positive, and I got two intercepts, 0 and then negative 3 over 2 right here. And so if we graph this, we got 0 and then negative 3 over 2, and so it's a quadratic that's basically opening up like this, so the vertex is going to be somewhere down there. But nevertheless, I mean, it's not symmetrical about anything, right? All right, if I take this half of the graph and reflect it, I'm definitely not going to get this half if I reflect it over the y-axis. And then if I reflect this in both axes, I'm still not going to get this half right here. Right, so just graphically we could tell that none of the symmetries hold. Axis symmetry is not symmetrical about the y-axis, or point symmetry. It's not symmetrical about both axes. So graphically we could tell that this function is neither even or odd as well. Moving on to part C, we have f of x equals sine x. This one I'm going to go about it in a different way. I'm actually going to draw the graph first so we could see, because to do it algebraically, you actually have to know a trig identity, which I'm going to introduce to you in a sec. So with the parent function sine x, I just want to look at the graph first. So if you remember from grade 11, right, sine x, it starts at the axis and then goes up like that. And actually, yeah, you know what? Maybe it's better to just leave it there. I know that a full period is going to be like that. But let's just leave the graph like this for now, because it's going to be easier to show what's going on here. Okay, and so just graphically looking at this, okay, if I take this half of the graph and reflect it about the y-axis, I would get this. I would not get this other half. So I know it's not even, but if I reflect this part over the x-axis, then I will get this part, right? So basically, taking this half, reflecting it about both axes, you could have also reflected it about the x-axis right? But I wanted to do the y-axis first to show it's not an even function. But we could have reflected about the x-axis and then the y-axis to get this other half, okay? So it basically has rotational symmetry, or it's symmetrical about both axes, sine x is, okay? So sine x is actually an odd function, okay? And then if we extend the graph, I know this extends infinitely, right? If we extend over here, right, that would do one full period. This would be up until 360. Well, the property still holds, right? If I take this whole thing, reflected about both axes, I would end up with this other half right here, and this would end at negative 360. Okay, and then this keeps going infinitely forever towards negative infinity and positive infinity. Okay, so graphically, you could tell that sine x, the parent function sine x, is indeed an odd function. Now, to do it algebraically, I mean, you just have to know there's an identity where, if you remember trig identities from grade 11, where sine of negative x is equal to negative sine x. Okay, that's basically an identity that you have to know in order to show it algebraically. And so then if we went through the process, right, if f of x equals sine x, well, f of negative x would be, we would plug in negative x for the x value, so we'd have sine of negative x. And then using this identity here, notice that sine of negative x, which is what we have here after we plugged in the negative x, that's equal to negative sine of x, like that. Well, that's the same as negative the original function, f of x, right? Because the original function was this sine x. And so f of negative x is equal to negative f of x from this identity. And so this property holds, right? It is odd. Okay, so this one I wanted to do it graphically first before doing it algebraically, because you do have to know this identity in green. That's what's used to show it algebraically. Now, what about part D? So f of x equals cos x, the other parent sinusoidal function. So same thing. Let's graph it first, because in order to do it algebraically, we're going to have to know an identity. So if you remember cos x, it starts at the maximum, right? And so it goes down like this and then comes back up. That's when it makes a full period, right? This is 360 over here. Well, over here it goes the same way. Looks like that. And so a full period there, negative 360. Okay, so this is how cos x looks like, and then again it extends, right? It keeps waving infinitely, right, to positive infinity and negative infinity. But let's just look at this to see the property here. And if you notice, this half of the graph, if we reflected just in the y-axis, we would get this other half right here, right? And so cos x is symmetrical about the y-axis, just about the y-axis. And so we could tell just graphically that cos x is an even function, right? Just graphically. And then if you extend this both ways, right, infinitely, doesn't matter if you took that whole infinite extension on the right side, reflected it over the y-axis, you'd get that other infinite extension on the left side. So cos x is an even function. And then algebraically, there's an identity you have to know where cos of negative x is equal to cos of x, like that. And so from here you could tell that this is going to hold, right? So like if f of x equals cos x, well, f of negative x would be cos of negative x, right? We would plug in negative x for the x values. And then cos of negative x over here from this identity that I gave you, that's equal to cos of x. And that's equal to the original function, right? So f of negative x equals f of x. And so we know it's an even function. That property is holding, right? But for these parent functions, sine x and cos x, it's helpful to look at it graphically. It's easy to tell that sine x is an odd function, cos x is an even function. Now moving on to part E, this is going to be a complex function. So we got f of x equals sine x plus 2x. Now we're going to use that same identity for sine x that we used before. Let me write it out again. So sine of negative x is equal to negative sine of x, right? So when we do this algebraically, this identity, pretend that it's just given to you. Okay, now graphing this, it's too complex to graph. You take this in Desmos, it looks crazy. So we're going to have to do this just algebraically, right? So going through the same steps that we did before, first thing we do, f of negative x. We have to find an expression for that. So we're going to plug in negative x for all the x values here. So we would have sine of negative x plus 2 times negative x, like that. Well, sine of negative x, using this identity, we know that it's equal to negative sine of x, and then 2 times negative x would give us negative 2x. And so that right there is the simplified expression for f of negative x. So first thing we check, is f of negative x equal to the original function? Well, no, it's not, right? This f of x sine x plus 2x is completely different than negative sine x minus 2x. So both of these do not equal, so we know that it's not an even function. Okay, what about this check here? Well, we already have f of negative x, so let's find this expression, negative f of x. So if we do this down here, negative bracket f of x, well, all we have to do is plug in the original function f of x sine x plus 2x in the bracket, distribute the negative sine x minus 2x, like that. So this expression in blue here is the expression for negative f of x. Now, is this and this equal? Yep, they're both equal, right? Negative sine x minus 2x, negative sine x minus 2x. So this does hold, right? So we know that this is an odd function. Okay, and then if you graph it on Desmos, you could see as well, it's something crazy. If I remember correctly, it's like a wave that's kind of going up like that. But then there's a wave that's going down. And so basically, if you reflected this in the x or in the y-axis and then the x-axis, you would get this half. Or if you went the other way, right? If you reflected in like the x-axis and then the y-axis, you'd end up with the other half. So you could see in Desmos, if you were to take this and graph this, you could see graphically that rotational symmetry or that symmetry about both axes does indeed hold, right? But if you were given something like this, there's no way you'd be able to know how that graph looks. It would just take too much work to figure that out. So you do have to do it algebraically, but while you're doing it algebraically, you do have to know this identity in green. Now, part F, we have an absolute value function here. So f of x equals the absolute value of 3x minus 5. Now, a property that I'm going to be using, I've mentioned this property before, but in an absolute value, if you have two things that are multiplying, you could take both things to their own absolute value separately and then multiply them like that, right? So I am going to be using this property when I algebraically show whether it's even, odd, or neither. Okay, so we have f of x equals the absolute value of 3x minus 5. So what we need to do now is find what's f of negative x going to be. So we're going to plug in negative x for the x values, like that. And so here we would have the absolute value of negative 3x minus 5, like that. And then to make it more comparable to the original function, what we want to do is inside the absolute value, we want to actually factor out a negative 1 because we want to have it like this 3x over here, right? We want to have the 3x alone. So I'm going to factor out a negative 1 from negative 3x minus 5, and I would be left with 3x plus 5, like that. Okay, and so from here, notice I could use this law because there's two things that are multiplying inside an absolute value. So I'll have the absolute value of negative 1 times the absolute value of 3x plus 5. Well, what's the absolute value of negative 1? It's just positive 1, right? Any negative in an absolute value turns into a positive, and so we're just left with the absolute value of 3x plus 5. Okay, so this is f of negative x. It's going to be this expression simplified right here. Right, so first thing we do, compare it to the original function f of x, which is the absolute value of 3x minus 5. Well, this and this, they're completely different. Right? Absolute value of 3x minus 5 is not equal to the absolute value of 3x plus 5. So we know that this is not going to be an even function. Now, what about an odd function? So remember, odd function, we already have f of negative x here simplified. So we just have to get negative f of x. Well, it's just going to end up being negative absolute value of 3x minus 5, like that. Okay, and we can't like distribute the negative inside the bracket or anything like that. And so basically, this is the simplified expression, right, for negative f of x. And notice that this and this, they're completely different functions, right? They are not they're not the same, and so we know that this function is also not odd, right? So this function in particular is neither odd or even. Now, if you're interested to see how it graphically looks like, if you remember your transformations from grade 11. So notice that the parent function is the absolute value of x. And if you remember the absolute value of x, it looks like this, right? It's just a V shape. And so to get this in the proper transformation format, again, we're going to go through transformations in a few sections again. But it basically looks like this. So this 3 means that it's horizontally compressed. That's the k value. It's horizontally compressed by a factor of 1 over 3, we flip it, and then x minus 5 over 3 means that we shift it 5 over 3 units to the right. And so this vertex on the parent function, it's at 0 and 0. Well, now the vertex is going to be at 5 over 3 and 0, right? It got shifted over, and then it got compressed like that. So it looks like this basically, it just extends infinitely like that. And just graphically we could see, right, this is definitely not symmetrical about the y-axis or both axes, right? So just graphically it's very obvious it's neither even or odd. All right, so this is, if you get an absolute value, this is the property here in green that you want to use when you're algebraically showing the symmetry. And that is the end of the video. Hopefully you enjoyed that. If you want to find more videos like this, you can go to my website, allthingsmathematics.com. Over there, all my courses are organized for both high school and university. All the videos are organized by chapter. Also, if you have any questions, you can hit me up. My contact details are also on the website. Enjoy your day, and I'll catch you in the next one. Peace out.